Fragmenters, and welcome to another video. Today it's Advent of Code. It's that time of year again, and I really want to see your solutions, so leave those in the comment section down below. If you want to support the channel, there is a link in the description to different affiliates where you can get great deals on things, and there's also a donation link if you want to donate a coffee to me in order to improve the quality of the channel. Day 9, Disk Fragmenter. Another push on the button leaves you in the familiar hallways of a friendly amphipods. Good thing you each somehow got your own personal mini submarine. The historian yet away in search of the chief, mostly by driving directly into walls. Smart. While the historians quickly figure out how to pilot these things, you notice an amphipod in the corner struggling with his computer. He's trying to make some more contiguous free space by compacting all the files, but his program isn't working. You offer your help. He shows you the disk map, your puzzle input. He has already generated, for example. The disk map uses a dense format of representing the layout of files and free space on the disk. The digits alternate between indicating the length of the file and the length of the free space. So the disk map, like 1, 2, 3, 4, 5, would represent one block file. 2 blocks of free space, 3 block file, 4 block free space, and then 5 block file. A disk map like 90909 would represent 9 blocks of files in a row with no free space between them. 3 9 blocks of files with no each file on disk also has an ID number based on the order of the files they appear before they are arranged, starting at ID 0. So the disk map 1, 2, 3, 4, 5 has 3 files, 1 block file with ID 0, a 3 block file with ID 1, and a 5 block file with ID 2. Using one character for each block, where digits are the file ID and dot is the free space, the disk map represents individual blocks. The first above represents these 3 individual blocks. Okay. The amphipod would like to move file blocks one at a time from the end of the disk to the leftmost free space until there are no gaps remaining between the blocks. For the disk map 1, 2, 3, 4, 5, it looks like this. The first example requires more steps. The final step of this file compacting process is to update file system checksum to calculate the checksum, add up the result of the multiplying each of these blocks' position in the file ID number it contains. The leftmost block is 0. A block contains free space, skip it instead. If a block contains free space, skip it instead. Okay. Continuing the first example, the first block block's position multiplied by its file ID number is 0 times 0, 1 times 0, 2 times 9, 3 times 9, 27, and so on. In this example, the checksum of the sum of these are 1928. Compact Antipod's hard drive using the process he requested. What is the resulting file system checksum? Okay. This is going to be interesting. Be careful copy pasting the input of this puzzle. It's a single very long line. Yes, it is. And I guess the IDs can be multiple numbers and so on. And then we have blank spaces, which could be a bunch of numbers as well. So, what do we do? We're gonna create a long list and work with that list, I guess. And then pop values from the end of the list, I guess. So, there is a stack as well, so we can dedupe and so on. But I'm not sure if you can insert at the particular position in that. So let's start with a list. And there is probably just one line. So lines get 0. And then split that. So we will get characters. For string character, like that. And then we have a list of integer. Disk, new array list. So here, for each character, we take character and create an integer of that. Num in integer parse int character. And then boolean space false, and then space is not equal to space. What? Can't we switch it over like that? We do that like that then. Let's see. If space, we do that, else we do that. For I 0 I less than num I plus plus disk add -1 int id equal to 0. So here we will take, no, here we will take id plus plus, and here we will add id instead. So if we string out here and pause, we should have a list of a lot of numbers. Yeah, that looks pretty much fine. So now we have the full length of the list. Now we need to compact it, starting from the end. Disk size. So now we will go through the whole disk size, and if we get this, and this is equal to -1, so we have an empty space, then we will take disk get disk size -1. While val equals to -1. We do that. Int val equal to -1. Disk. Oh, if we do a remove, we will get the value as well. So that's even better. So we do like that. Remove a bunch of values from the end until we get the value. And then we will take disk, add at I position val. So this could work, but I'm not really sure if it will remove the value as well, or if I need to do that. So we want to stop there. So that's the first, index 1. So now we have a 9, we have index 1, and we index 2, and we have the disk. We have 3 1s here. So now we just move those down. So that will not work. So first we need to remove that and then add it. So if we do like that, everything seems to work. And if we are here, we have 28 spaces. And it seems pretty reasonable. So now we need to do another loop through these. And add them up, pretty much. Int count. Let's do a long count. No, not even that. We do a big int, because we're going to do multiplication, so this could be really, really big. Big integer 0. Count is equal to count add big integer of value of EI multiplied by big integer value of disk get I. So what do we get then if we print out count? That's the question. 1928, which seems to be our number. So let's see if we can unleash the large number here. Okay. We ran out of disk space. We can return here. And we still do the break, but we take disk and we add the value back. Then we will get a little bit larger number, I guess. Yeah, it's a little bit bigger. So let's try that instead. Yes, you get a gold star. I get a gold star. Everybody gets a gold star. So now I solved part 1. Part 2. On completion, 2 things immediately become clear. First, the disk definitely was a lot more contiguous free space. The the disk definitely has a lot more contiguous free space, just like the Amphiphod hoped. Second, the computer is running much more slowly. Maybe introducing all of the systems fragmentation was a bad idea. Introducing all of the systems fragmentation was a bad idea. Eager, the Amphiphod has already a new plan. Rather than move individual blocks, he like you to try compacting the files on the disk by moving whole files instead. This time, attempt to move the whole files to the leftmost span of free space block that you can fit the file. Attempt to move each file exactly once, order of decreasing file ID number. Starting with the file with the highest file ID number, there is no span of free space left on the file at large numbers. It does if there isn't any space, then don't move it. Okay. The first example above proceeds. Then you get 2008.58. So it's pretty much the same, but we will move the full file instead. Yes. So we pretty much need to figure out the block count instead, and we can update the list from there. So I think we need to have a totally different solution for this. So let's copy this one, call it B, but we use the same input data. I think we can have a new class called block. And this could have int size. It could be public. Public int size. And then public ID. Shows it correctly when I generated it, but I didn't. So let's see. In this, we need a disk of block instead. And here we will add new block. And it will have a size of that num and ID of -1. And then we will have disk, and this will have an ID of ID. Very simply. While boolean decompress true while decompressing. So we will remove all this. Down here we'll do a count. Disk get I block if block get ID is not -1, then we will add to the count, and we just change this over here to get block ID, create that method, return ID, and it can be it. Doesn't matter. So there we go. Now we have that thing done. Found space. We found a space. So disk get disk on disk disk place disk size -1. So disk remove disk place block work. So this is the work block. If work block get ID is equal to -1, then we will just take disk place and decrease it. Else we'll try to find a space for this one. For each block in we need to use the ID then in the I0 I minus disk size I plus. We go through all the disk block and we will check for a space. And we will get I. Possible space. So, if possible space get ID is equal to -1, then we can do something. Possible space get size. Now we can just do try to fit. Work block. And then we will get a list of block back. And if blocks size is larger than 0, then we will do disk remove I and disk add I blocks. Get 1, get 0. So now we'll add those in if they fit. So here, if the work size is smaller or equal to, oh, we could have 1 block left. Now that's no good. So if blocks not null. So now we will go j larger than 0, j minus minus. So we will go from the back and add the blocks because there could be 1, could be 2 or 0. 2, 1 or 0. So if work size is equal to this size, if that is true, return work as a list. List block new block new list new array list. So here we will have a couple of different options. If work size is larger than this size, we will of course return null. Else we will have this new list add work and return new list. And we also have the last case here, when it's smaller, because it either is larger, then we return null, or it's equal to, or it's smaller. In the case it's smaller, we want to return both, but we want to return the space afterwards. So we will have the same thing here with the new list. What happened? I just want those 2 lines. And then we also have a new space. So we will take new list, add new block of the size of work, this size minus work size minus 1. So now we will have a new block there. So what do we get then? We get an array out of bounds again in both cases. That's lovely. In this case, when we have added a new block, we need to have disk place minus minus. And we also need to remove disk place. So we need to we don't need to remove disk place, but in the case where we didn't, here found space should be false, and then here found space should be true. So we found a space and we replaced it, and after this loop, if found space is not true, then disk place minus minus and disk add work. I think we can move it like that, so always decrease disk place. 480. So that's not correct. Close, but no, not really. And we are back, and I have debugged a bunch and figured out a bunch of things that I did wrong. And I also had my morning meet for my company, so I'm gonna start work soon. So this is just seeing if I found the right solution. If not, then I pretty much need to figure more of this later this afternoon. So the big changes here is, first off, we have the block up here that we are creating. And then when we come down here, we don't remove the thing at disk place. So we are just getting the work block here. And then we will decrease the placement that we have. And then we have the found space, if we found a space for it. And then we will go through the full disk space and see if we can find a possible place. So that is this thing here. And if we find a possible place and it fits, and we don't get nullbacks, we have fitted in, then we of course need to remove the old disk space and replace that with a space. So we remove the block that had data to get it somewhere else, but we get a new empty space there. And then we remove the current block that we want to use here. And then we go through and add the new blocks. And here, after I said that I found a space, I thought maybe I need to merge the space blocks. And I could do that. The problematic part is that then this 888 over here will move in here, and that is not allowed for some reason. So I just skipped that, and then I got the right result. Maybe there is something there, so I could look into that. But yeah, currently I don't do that. And then I set disk space to the last position, so I start all over again. Maybe that is not allowed, then this would be solved anyway. So there is a couple of complications here that I could look into later on. And then we check the next space here. If we don't find anything, then we need to move on. So that's it. And then I print out, so I see the actual one. And then I calculate it down here. So I take, here was another thing that I had wrong. First off, we need to calculate from the actual placement. And then I go through each of the blocks. If it's not the space, then I need to go through and add up the multiplication for each placement. Otherwise, I need to add to the placement because the empty space will also change the actual placement in the count. So this gives the right result for the small test case. We will try with a large test case. If this doesn't work, I need to figure out another way of doing the merge and resetting where my position is. But it could be correct. So let's try it out. So there we go. Got a large value. Let's see if that is the right value. Yes, you get a gold star. I get a gold star. Everybody gets a gold star. So let's do a quick recap what we actually did. We read in the lines up here. We create a block list, which is our disk. So this contains of either empty blocks or blocks with data. We go through here and find the space and the block data, and that is done by either or. Even is blocks and the odd ones are spaces. So we go through each one and take the numbers and create a long list of blocks and spaces. Then we will take the last position of this and start and see, can we get down to 0 here? So we start from the end of the list and go down to 0. We fetch the first block and say that this is our work block. If the work block is just empty space, we just decrease our counter so we get, so we take the next block and check that. Else, we will see if we can find a space where to put this block. So let's go through and see if we can find a possible space. We go through from the beginning to the end and take out a block of possible space. If it is a space, then we see if this block can fit in it. So we run the fit function and we get either 1 or 2 blocks back or null. If we get null back, then we know we didn't find a space. But if we don't, then we first off need to remove the old placement of this block that we need to move. We need to add an empty space in that position of the same size as the work block. And then we need to remove the space that we want to replace with the block of data. And then we will add either 1 or 2 blocks in that space. And because of the way we ordered the block when we put them in the fit function, we need to do that backwards, because when you add something, you will push everything backwards in the queue. So that's why we are running this function backwards, and we add, and then we say that we found a space. I thought that we might need to merge empty space, because you could get the situation where you put something in and then you have either before or after a space, and those aren't merged to one good space. So, but if you do that, then more blocks will be moved and it will not work with the set out assignment. And then we will start over from the end of the list. So we are running this over and over again to find blocks to put in a good position. And if we didn't find a place, we just decrease our disk space. I have a little thing here for debugging where I print out the space and the actual ID, so I can see a long list of all the values. It's not that helpful when it comes to the full data, but for the small example, it's very useful. And then we last off have the count here, where we start with the big int count at 0. We keep track of the placement of the actual value in the series, because the data should be multiplied with the placement. So we go through the disk, full size, we get 1 block. If this block is not empty, so it's not an empty space, it has data, then we need to count up the multiplication of the placement and the ID of the data over and over again for the block size. If not, we need to just add to the counter of placement, so we don't miss out of where we actually are in the data list. And then we print out the count. So this was day 9 of Advent of Code. I didn't like that we didn't have to merge the space blocks. I would really like to see that, but it was not in the assignment. If you have any other solution, please leave a comment in the comment section down below, so we share with the rest of the community all great solutions that we have. If you like this video, give it a like, share it with your friends and colleagues. If you haven't subscribed yet, please do that. And I really hope to see you in the next video.